So let's have a look at this idea of internal forces and how they help forces get from one place to another. So let's have a look at this example first. So we've got something here, it's a fixed ceiling or something like that. You've got a 2 kilonewton weight on there, so it's got a weight of 2 kilonewtons, so it's got a mass of about 200 kilograms, something like that. And so if that's under gravity, that's going to mean that there's a load of 2 kilonewtons acting at the bottom here, well, acting from the center of gravity of that, actually. Let's just move that up so that's the case. So it's acting from the center of gravity. Try not to take the bottom of it with us. Okay, so you'd have 2 kilonewtons acting down the way. And for that to work, you must have a reaction. So this is kind of, you could do it by particle equilibrium. It's a bit of a trivial situation. You must have an equal and opposite force at the supports. So this force essentially must be transmitted up through this tie. So this is a tie, it's in tension, through this tie to get to the reaction so that they can cancel out. And the reason it can do that is because of internal forces in this structural member here, so this tie here. So it's got internal forces. How can you, so you can't see those forces, you can't touch them. The way you usually think about when you're looking at trying to figure out what forces exist, often a useful technique is to imagine cutting it and to think about what would happen. So what would happen here is that this would fall down like so. So you imagine pulling it apart. And so what must be here is there must be forces acting across that section that stop this from separating. And you can kind of think of, I'm going to show you this in a bit more detail later, but if I spread this out a little bit more, to stop this falling, what we must have in here is we must have an internal force that's keeping this from falling down, so it's equal and opposite, so 2 kilonewtons up the way. And now what we can think about is, if we have this force here, we ignore the fact that this is fixed. If we have this force here, then if there's nothing balancing that force, it's going to end up shooting up the way. So there must be another force acting down the way on that end. Okay, and we can see those if we split it apart. But those forces must be acting across that section. Those are internal forces. In this case, we'd call them tension. Similar idea for a beam. If you had a beam, you've got an applied load. We're just ignoring the weight of the beam. Somehow that force has to get from here to the support and from here to the support. If we were to cut that beam, so you can't see those forces, they're internal forces. Okay, so these ones we've drawn arrows for, those are all external forces at the moment. What you can do though, to try and figure out what internal forces there are, you can imagine cutting it and then think about, oh, let me just say one more thing actually before I go on with this. What you can tell in the other way, so one way is to cut it and imagine equilibrium on both sides. The other reason you can tell there's internal forces is because the shape of, or the dimensions of the object are changed, it's deformed. Let me see if I can get this back to where it started from. Or have I gone too far? I have gone too far, but let me put it back to where it started from. So it was there, imagine we haven't cut it. But if that load was on there, what you can imagine, it's exaggerated here, but you can imagine it's going to stretch this tie a little bit. That's the other reason we know that there's internal forces in here, because the shape of that object, that member, structural member, has changed. Okay, so for the beam, it's a similar thing. If you were to apply a load here, and we've got reactions here that balance this load, so they must be, the sum of the y components of these must add up to the total applied load. What would happen to that beam is it would bend a little bit, so you're going to get it deforming like this. And so we know there's internal forces there because this object has deformed. This time I'm not going to go into the details, this takes a bit more explaining, but again, you can imagine if we cut it, what would end up happening is you'd have one piece would fall down like that. The first thing is it wouldn't be bent anymore, it would straighten itself out because there's no internal forces in it anymore. And the other side would fall down like so, so it would be straight as well. You've still got the force on here. Again, the whole thing would fall down. So here, to stop this falling down, there must be some kind of internal forces acting across this section that we've imagined cutting. And so the way we can think about those is to figure out what forces would we need to apply to these, the ends of these sections, to make it go back to what it was originally. So it's curved and it's not falling down. Okay, so that's the kind of idea of internal forces. You can think of it in lots of different ways. Internal forces are how applied force gets to the reactions, and so it's how the force is transmitted through the body. You can kind of figure out that there must be internal forces because if you cut it, it would fall down. So the internal forces are what you would need to mate those two surfaces together again, to get them to hold together, if you figure out what forces you'd have to apply. And the last thing is we know there's internal forces in a body if the body is deforming. Now, you might not be able to see it deforming. It might be too small for you to be able to see it, but that's how you know there's internal forces, because there's a deformation. Now, the next thing I want to show you is the three different types of internal forces and what deformations are associated with them. So what I've got here is two forces. So those are external forces. We're going to apply these to this structural member, which is made of foam, so that it's nice and flexible so we can see what's happening. So we apply two forces like that. You'll know what you're going to get is tension. What does tension do to the body? Well, it makes so what I've done is draw a grid on here. If you were to draw little squares, it's a bit rough, but you get the idea. So I'm applying the two forces that I was showing you here. So those two forces, let me move that out of the way, try and put them straight. So I'm applying those two forces. So if I pull this like this, what you can see is those rectangles get longer and thinner. Okay, so they're getting longer and thinner. That type of deformation tells you that the internal force is tension. On the other hand, that's called an axial force tension. There is another axial force, which is compression. So our external forces would act like this, pushing this together. This is a little bit harder to show because what will happen, so I'm going to do the same thing. It's a little hard to show because what happens is, you can see it there, it buckles. Now, buckling is something we'll look at, or you might look at in another class. If I try and restrain that buckling, it's a little hard to get this to work because I haven't been careful enough about cutting this, and it's hard to not buckle it. Maybe I can just go a little bit less. You can maybe see just a little bit. What's happening is those squares are getting shorter and fatter. So tension, longer, thinner. Compression, shorter, fatter. Now the fact they get fatter when you're compressing it and thinner when you're stretching it, that's called, that effect is described by Poisson's ratio, which is another thing you'll learn maybe as you go on through engineering or construction management or whatever you're studying. But those are the two axial forces. Okay, if the external forces are both pulling out the way like that, you'll get tension. You can tell there's internal forces because the shape is deforming. If you had two forces going the other way, you'd be getting compression. Okay. The next type of internal force, we'll do the same one, is called bending. So that would happen if you applied, now let me just try and get all this the right way around, if you apply a pure moment at each end. Could even put it on the out, so it's going to be on there. Let me just put it here so you can see it. Okay, so we're going to apply a pure moment at each end, and those two moments are opposing each other. Okay, this one is negative, it's going clockwise. This one is positive, it's going anti-clockwise. So those are the two external forces. I'm going to apply pure moments to the end of it, like so. Now, you could think about that. Let me just think about what way we're doing it. You could think of that as a couple. So it's a couple moment or a pure moment. Okay, just showing you that so that you're, okay, so, and I'm going to do that with my hands. And so I'm just creating two moments at each end of that beam. And what I might do, no, it's not going to be exact, but see with those pure moments, what you can see is at the top, the squares are getting shorter, whereas at the bottom, they're getting wider. Okay, they're getting longer. What I might do is I should be able to, it's not exactly the same this, but it gives a similar effect. I'll just put in a couple of supports here with some matchsticks, and I'll apply a load with another matchstick. So it's not exactly the same because this is a point load, but you can see these squares here, they're getting wider in the X direction. These squares here, they're getting shorter in the X direction. And because this is a point load, you get some unusual effects, just local effects here. So the reality is never quite as simple as the theory, but it's a lot tighter if you apply pure moment at both ends. That's really pure bending. pure moment at both ends, you can see for a lot, until it gets to the point where we get some local buckling, the squares at the bottom are getting longer, squares at the top are getting shorter, that in the x direction. So that's bending. Could do it that way, could do it the other way, could be like that. Again, in both cases, I'm applying a couple. Oops, applying a couple. This couple's in the other direction. So that internal force is called bending moment. Okay. Yes, called the bending moment. The bending moment of this. Okay. So the internal force, so the external force is just called a moment or pure moment or a couple moment. The internal force is called the bending moment. And that's how it's distinguished. So that tells you that's the internal force that you're talking about. It's this force that causes the squares, the x part of the square, to stretch at the bottom and compress at the top. Okay, bending moment, that's the second internal force that we're going to look at. Third internal force is shear. Now, you can't do shear with these. That there, well, I won't confuse you by saying that. So what we're going to do for shear is we're going to push, I'll try and do positive first, which I think is that one. I'll talk about the signs in a minute. So we're going to apply forces at each side in opposite directions. Looks a bit like a moment, but it's not, well, it is a couple really. It would tend to cause this to rotate. But what you're going to do is you're going to fix it in position. And so what we're going to keep them in the same direction, if you know what I mean. And so if this was a couple, it would be free to rotate, but I'm kind of defining this so that they have to stay in the same direction. They're not allowed to rotate. And what you get when you do that, if I try and do it so I have to try and grip the whole edge to get this to work. And if you ignore the local buckling and the local effects, what you can see is the squares become little diamonds. Okay, so they become, well, rhombuses, like so, especially if you look near the center of the foam. Okay, so the squares are becoming diamonds. And so that's shear, the internal force that's associated with that type of deformation. I need to try and keep them parallel to make it work. That is shear. There is one more internal force, and that happens if you apply a pure moment on the end, like so, and then you do one in the opposite direction at the other end, and it deforms like this, and that's called torsion. Okay, that internal force is called torsion. But we are only looking at two-dimensional problems, so we're not going to come across torsion in the examples we're doing, but you need to be aware of it. So that's called torsion, where you twist the bar like that. So just to summarize those again, we've got tension, axial force, compression, can't really show it, but compression, axial force. We've got bending, and it's hard to show bending with a thin member like that. We've also got shear. A bit untidy, the shear, because it's hard to grip it uniformly the whole way along, but that's shear. Okay, sign conventions. So you'll remember for a moment, what will I start with? We'll start with tension. Let me move all the other bits and bobs out the way. So for an external force, so this force here, this force is heading, so you might have x, y, let me just do it with these ones. You might have x and y going in this direction, so x is positive up, sorry, y is positive up, x is positive, pointing towards the right. Okay, like so. So that would mean this force would be positive, this external force. This external force would be negative. However, when it gets to internal forces, it gets a little bit more, not confusing, but a little difficult. Because to make this internal force, this tension, you need positive and negative external forces. So it's no use using those. What you've got to think of is that you've got the two forces are away from each other. You've got a positive force on the right, negative force on the left. And so that is positive axial force. Okay, so it's a positive axial internal force. Well, I'm squashing it, which confuses the issue. I'll squash it the other way so you can't see that. Okay, so that's a positive axial force tension. Negative axial force would be compression. You don't have to take it that way. In fact, if you're doing a problem that's all got all compression in it, often you'll take compression positive. But in this course, the default will be this is positive axial force. This, when I'm squashing it, is a negative axial force. For bending, so again, your external forces, let's think about this. So this would be this one on this side. That's clockwise, so it'd be negative. For this external force, that's anti-clockwise, so that would be positive. But when we're thinking about a bending moment, this internal force, what we say is when it's bending this way, down the way like that, that is a positive bending moment. And it's also called a sagging bending moment. So if this was a beam, that would be the beam sagging. Okay, so it's sitting down the way. And so that's a positive moment, is sagging. Negative moment is like that. That's a negative moment. And it's often called hogging. So we've got sagging, positive, hogging, negative. Let's start bending. For shear, let's have a look at this. Let me just have to remind myself of what's positive for shear. So if we've got up, left, down on the right of the object, so up on the left, so this would be a positive. Oh, I've knocked away, I've stolen my axes. So we're keeping the same axes like this. So we've got a positive external force on this side, a negative external force on that side, and it's going to produce shear like that. So positive on the left, negative on the right. That's going to be a positive shear for the internal force, a positive shear. A negative shear is going to be down on the right and up on the left. So that's going to be a negative shear. Okay? And so if you look at your object, look at the forces on each side of it. If it's going up at the left, down on the right, that's positive. If it's going down on the left and up at the right, that's a negative shear. Okay, so now what we're going to do is look at the mathematical ways we use to find the magnitudes of these internal forces.